I'm just going to make this slightly bigger. All right, so if you can, please turn to example 6. So remember yesterday, we talked about a lot of things actually. We talked about determining if a function was linear or nonlinear. We talked about, I hear a lot of voices still. You good? We talked about intercepts. So identifying intercepts from our graphs like this. For nonlinear functions, we had multiple x-intercepts that we had to list out. So let's look at example 6. This is still an intercepts question, but now we're talking about intercepts from a table. So this is a really classic parabola problem where you think about like a projectile motion. It makes a parabola. So Ricardo launches a rocket from a balcony. Hold on, I still hear a lot of voices. I have to shout over my 4-year-old enough, so. Can you sit over there? So Ricardo launches a rocket from a balcony. The table shows the height of the rocket after each second of its flight. So to start, we want to identify the x and y intercepts of the function that models the flight of the rocket, and we want to think about what those mean. So just as a reminder, you can look back in your notes if you want. X-intercepts are always a number, comma, 0, right? So as we look at this table, remember our x-intercepts are going to be a number, comma, 0. Where 0 is like our y part of the coordinate. So if you think about this table where time is your x and height is your y, do you see a coordinate point in that table where you have a y that's 0? Do you see a y that's 0? Yes. Where is it? At 8. So that's how you can actually see an x-intercept just from the table. So our y-intercept, likewise, will be 0, comma, a number. So where do you see an x that is a 0? 15, where my height is 15. All right, so what do those mean? Remember, he's launching a rocket from his balcony. So let's look at the x-intercept. Actually, let's look at the y-intercept first. That one's a little easier to think about. If our x is 0, x is time, this means when Ricardo starts to launch, how high off the ground is he? He's 15 feet off the ground. So this y-intercept represents the height the rocket started. The height the rocket started. So what does our x-intercept represent, where it's 8, comma, 0? It's what? It does lie on the x-axis. So after 8 seconds, what do we know about the height? It hit 0. So we hit the ground at 8 seconds. So when the rocket, say, landed. When the rocket landed. All right, for the sake of time, I do have in my, and I'll post the notes with this all done, I do have this like all the way where we're counting by 15s and we're going to model the rocket, but let's just kind of make an unofficial picture for time's sake. If x is our if x-axis is time, we go from 0 to 8, so 0, 1, 2, 3, 4, 5, 6, 7, 8. And then we have to go up to 210. And again, I'll post a copy where I do all the little tick marks, but let's just kind of pretend here. Basically, what's going to happen is we don't start at 0. We would start at 15 down here. So if I were to draw how this projectile moved, it would basically be like that. So sometimes looking at the picture can give us some context. And in fact, one thing we don't talk about with intercepts that we'll talk about in the next section is this point right here, which I don't know how accurately I drew this. 1, 2, 3, 4. I did it pretty good. That's like our maximum height there. So you can see that from a parabola as well, which if we were talking about a context of a situation, that could give us some information. Okay, what I want you to be able to take away from all of that, can you find an X and Y intercept from a table? Do you guys feel comfortable doing that? Okay. Can you make meaning from the table? You'll have a story problem. You guys can kind of practice with that as well. So let's talk about symmetry. Our next definition. So we say a figure has symmetry. A figure has symmetry if there exists a rigid motion, either a reflection, a translation, a rotation, or a glide reflection that maps the figure onto itself. Do you guys recognize those words from geometry? Hopefully. So that's what we're talking about. And we're not getting too much into it. We're not going to talk about like a reflection about the 0.32. We're just going to talk about, is it a reflection? Is it a line symmetry? So if you look at this first example, this is a parabola. This is sort of like our butterfly example. This is called line symmetry. And I'm just going to, you can circle the words if you want, but line symmetry. A graph has line symmetry if it can be reflected in a vertical line so that each half of the graph maps exactly to the other half. So that's this orange line right here. That's the line of symmetry. And the idea is that it's the same on either side. So then we say a graph has point symmetry, and this one's a little harder to see, when a figure is rotated 180 degrees about a point and maps onto itself. So really quick, 180 degrees, that's not a full rotation, because remember a full rotation is 360. So it's saying halfway. So basically, if you looked at this picture here, this has point rotation about the origin. You can think of it as taking this upper blue arrow and pulling it down to that lower blue arrow, and it'd still be the same shape. That's 180 degree rotation. So that's our point symmetry. So let's see some examples of what this looks like. And we're going to actually come back to this page and add something. Oh, no, we're not. I have it on the other side. We're good. So example 7, and again, this is good news for you guys because I'm asking you what kind of symmetry it is. So when you do your homework, there is not really work to be shown here. You're just stating what kind of symmetry it is. So example A, there is no line that I could draw where I could reflect it over that line, it'd be the same. However, if I took and I rotated around this point, for example, 180 degrees, I would be back on that original point. So this has point symmetry. So example A has point symmetry. Example B. What do you think for example B? Say it loud and proud. Line symmetry. You can see that line. It's anytime you think of the butterfly shape, it's the same on both sides. So this is line symmetry. What about C? No symmetry. It doesn't have point symmetry. It looks like it almost could be line symmetry. But if you look, this is way lower than that point. So this has no symmetry. And then what do you think of D? It actually does have symmetry. Yeah, it's point symmetry. So you're looking for like this shape here needs to be the same but flipped there. So that's kind of what you're looking for there. So this has point symmetry. How do we feel about looking at symmetry? These are quiz questions, so hopefully we feel good about this because it's just using our eyeballs. Okay, the last thing we need to talk about is even and oddness. Last year we did this algebraically, and I'm going to show you algebraically, but we're going to talk about some rules for this that you can use those symmetry ideas to figure out if a function is even or odd. So what does it mean to be even or odd? Functions that have line symmetry with respect to the y-axis are called even functions. So basically, and I'm going to put here line symmetry over y-axis. So that's where the line symmetry has to be right on this line. Those functions will be even. There is an algebraic way to show that. The algebraic way to show this, and we're going to write this on the top of the next page too, but it's this rule right here where basically you can take the function and instead of plugging in x, you plug in negative x. And if you go through and you do the algebra, you deal with the powers, you see, do you get the original function back again? And I'll show you in the example what that means because it kind of sounds weird. But that's the algebraic way to show it. I'm okay with you guys today just looking at it and telling me based on this line symmetry, you might have to graph it. So today might be a day you borrow one of my calculators because some of the examples just have the equations. But I'm okay with you doing it that way as well instead of doing it algebraically. So if we have even functions, we also have odd functions. So the odd functions are where you're going to have point symmetry, but it has to be around the origin. So point symmetry around 0, 0. If it has point symmetry, but it's like to the side, so if this function, instead of being where it is, if it was over here, that is not an odd function. It does not have point symmetry around the origin. Again, algebraically, there is a way to do this. How we would do this algebraically is if you plug in a negative x into the original function, and you look at that original function, you just flip all your signs. If those match, then it's odd. So last example, and then I'll set you free, but this takes a little bit of time. Okay. So example 8, we have 3 graphs here, and we're going to make a prediction based on how these graphs look, if they're even or odd, but then I'm going to go through and show you the algebra for proving even or odd as well. So it can be even, odd, or it can be neither. Just like there are some graphs that have no symmetry, you can also have a function that's not even or odd. So the steps for this. So if you want to kind of squeeze this in on the top, your first step here, whoops, not with that one. Your first step here is that you're going to plug in negative x. You will have 3 things that can happen. When you plug in negative x and you go through and deal with your powers, either you will have, so if you get original, and I'm going to abbreviate here, fxn. You guys, are you okay with that abbreviation? That means function, fxn. It's just a short way of writing function. So if you get the original function, it's even. So you'll plug in negative x, and it's sort of like plugging in negative 1. You're just looking at the signs. You'll get something that's even. Give you 3. I don't know. You want 3? Just 1? Yeah. I'm going to do 3 colors. All right. If you get a function with all signs flipped, and I'm going to show you what I mean by that. All signs flipped, then it's odd. So if you get a function with all of the signs flipped, it's odd. And that's actually one thing I list out first. Is I just look at the function and I go through and flip all the signs because then we can compare. So if you get a function with all signs flipped, it's odd. And the last thing, if neither of those things happen, it's just neither. So I'm going to say otherwise, neither. So if you get the original function when you plug in negative x, it is even. If you get a function when you plug in negative x where it's all the signs are flipped from the original one, then it's odd. And if you get something that just doesn't match either of those, then it's neither. No, we're going to do example 8. So example 8, let's just look at this for a second. What kind of symmetry do you think this has? Point symmetry or line symmetry? It's point symmetry, and it looks to be about the origin. So we can make a prediction that this is probably odd. But let's see the algebra for why that is. Okay, so the first thing I do is I do go through and look at, if we just flipped this equation sign, so instead of x to the third minus 4x, if this was negative x to the third plus 4x, this is what we're going to compare to see if it's odd or even. Do you guys see how I just flipped both signs? I'm just comparing. This is nothing we're using yet. I just flipped my signs. Let's run through the test. So what I do is I take the original f of x, but instead of x, I'm going to put a negative x. So everywhere in that original function where I see x, let's put parenthesis negative x. So instead of x to the third, I'll have negative x to the third minus 4 times, instead of x, negative x. Okay, this is substitution 101. I know a lot of students don't like substitution for whatever reason. I like to color code it. Now, I have no numbers that I can do anything with, but somebody tell me, when you have a negative number raised to the third power, does it stay negative or does it become even? Or not even, positive. So think about negative 2 to the third power. What is negative 2 to the third power? It would stay negative, right? Because it'd be negative 2 times negative 2 is positive 4. Times a negative 2 would be negative 8. So this will stay as a negative x to the third. What about that negative 4 times negative x? What happens to the sign on that? It turns positive. So this is going to become plus 4x. Okay, does that match our original function? This one right here. Does that match? Look at the signs. No, the signs are flipped. Does it match the blue one that we did? Yes, so it's odd. So since it matches that one where we flipped all the signs, it's odd. That's algebraically how you do that. Now, we did it visually as well, but I'm going to show you algebraically because you can do this as well. All right, let's do another one. Following the same steps. So again, just looking at this, what kind of symmetry do you think part B has? Looks like line symmetry. And again, it has to be on that y-axis. So my first step always is that I'm just going to look at if I just change the sign. So instead of a positive 2x to the fourth, I'm going to make it negative 2x to the fourth. Instead of a minus 6x squared, I'll make it plus 6x squared. So I just changed my signs there.
Couldn't you tell by like the powers they use too?
You are exactly correct. So when I go to plug this in, instead of g of x, let's go ahead and plug in g of negative x. So I'd have 2 times, instead of x to the fourth, I'll have negative x to the fourth, minus 6 times, instead of x to the second, I'll have negative x to the second. And then as you just pointed out, we have some power things going on. What is negative 1 to the fourth? Is it a negative 1 or a positive 1? It'd be positive because anything to the even power is positive. So this 2 times negative x to the 4th is just going to be 2x to the 4th. What about negative x to the 2nd? It'd be an x to the 2nd. So this minus on the 6 will stay, and I'll have x to the 2nd. Does this match that blue function, or does it match the original function? It matches the original function. So for that reason, this is an even function. Do you guys have questions about these two? I like to show you the algebra just because I like to practice the substitution. Last one, and then I'm going to set you loose. Be really careful on this. What kind of symmetry does it look like this has?
It looks like it's point, but it's neither.
How do you know it's neither, though? It does almost look like it's point. I encourage you to count the boxes here. This little hump has a little over 2. This one box. Ooh, it's a little under 2 boxes. So you guys see how it's not quite? Now, would I ever do this on a quiz? No. This is, I will give you very obviously like not symmetric or point symmetry or line symmetry. This one's being a little sneaky, but this one should be neither. It should be neither. Let's go ahead and do the substitution, the algebra stuff. So just to start again, so that I can compare to see if it's odd, I'm going to go through and change all my signs. So this would be negative x to the 3rd minus 0.25 x squared plus 3x.
You've been meaning to record your voice.
It's recording on here.
It says you're muted on both.
No, it's muted on this one. Am I muted on both? I might be muted on both. I shouldn't be, but you're right. I think I am. Son of a gun. It's great. It's fine. It's all good. All right. So then I'm going to take this function. That's just breaking my heart. Instead of x to the 3rd, I'll do negative x to the 3rd plus 0.25. Instead of x to the 2nd, I'll do negative x to the 2nd. Minus 3 times negative x.
It's showing up on the top right.
I know, it's because like I'm sharing multiple screens, so I don't know. We'll see.
It's confusing.
I am confused. We'll see. It'll be a gamble. I'll try and play it later and see if I can hear myself. All right, negative x to the 3rd. Is that going to stay negative or is it going to become positive? It's to an odd power. So it stays negative. Any odd power will stay negative. What about that x, negative x to the 2nd power? Positive. And then how about that minus 3 minus x?
That'll go positive.
Positive 3x. Okay, does this match the original function? Does it match the blue function? No, look at that plus 0.25 minus 0.25. So this one is neither. Come on, turn it into a box. I didn't want to turn it into a box. It's fine. Okay. So for today's assignment, I would love it if you would practice that substitution stuff, but I am, again, not collecting work, so you don't need to. Let me post your assignment, because I don't think it's posted yet.